All right. Good evening or good morning, as the time zone may be. It's good to see you all. Let me know, especially tonight, whether there's any issues with audio. I think I've got it straightened out, but if I don't, I want to know about it. And for anybody who's watching this live or a recording later, you're watching the 5 Live Free Code School. I'm your instructor, Eric Gross. We have 5 live students in the classroom learning to become well-rounded, entry-level, full-stack developers, and you can learn along with them as well. Okay, so I'm going to take away the slide here and stop sharing for a moment, and we'll just talk through some things. Okay, so first things, we talked a lot yesterday about binary and how it works. And I assigned some homework to go through 8 of those transitions back and forth between binary and decimal and vice versa. Who got that done?
I did.
Yeah, I did too.
Excellent. Jonas?
Sorry, I haven't done that.
Okay.
As,
It's totally fine. We have all week. And Jason, how'd you do?
Yeah, I did.
Okay, good, cool. Jonas, yeah, let's get it done this week. And I don't expect you'll have a problem with it. I know you covered that in college, but it's been 5 years. If you have any questions at all, just ping me either on Twitter or if I get you into the Discord channel. Okay. Anybody have any questions that are outstanding from yesterday's material? All right, good. Okay, then we're going to dive into some stuff involving CPUs. Now, I just want to preface this that none of this stuff is coding, and you're taking a coding school. And again, I mentioned this right at the end of the class yesterday. It won't be very long till we're actually writing code, but I'd like you to have some understanding of when you write a program and it gets turned into instructions that the computer can actually work with. What does that look like? One of the primary things I really want to reinforce here is that legitimately a computer truly can only do one thing at a time. There's lots of paradigms you're going to see when you start to write code where it can look like things are happening simultaneously. When we come all the way down to where the actual CPU is, the central processing unit, it can only do one thing at a time. And I want you to see that from a mechanical and electrical standpoint, that literally there's no way for it to do two things at once. Okay. All right, let me pull up chat over on the other side here, and then I'll share material. All right, so I have chat on the other screen, and I'm going to try to watch that. I'm going to put it closer to my eye line. And if you chat something and I don't respond after a little bit, cut right in. Okay. All right, so let's start looking at some material here. We are looking at the idea of how a CPU works. And if we look at specifically my module session notes, there we go. What I want to look at today, from a high level, we're going to make sure that we really get any questions answered about memory. We looked at some fundamentals at the end of the day yesterday, why the CPU even needs it and the different types of memory. And then we're going to start to look at about 3 parts inside the CPU. There's a lot of parts inside there. You don't need to dive very deep at all. But the 3 parts that we're going to explore really show, 1, how the computer can only do one thing at a time, and 2, when it gets an instruction, what does it do with it? How does it actually work? And we're going to study a thing called the machine cycle. And all that is when you give an instruction to a CPU, what's the exact 3 things it does every single time, over and over again. And finally, we're going to bring it all together with the concept of the clock, a clock that exists on every single CPU, or rather, usually exists on the motherboard, adjacent to the CPU. And we'll explore what that is and why it's important and that sort of thing. Now, a question, in reading You Are Not Stupid, has anybody gotten to this section where we described how these looms for making fabric worked back in the 1700s? Okay, has anybody not reached that point in the book yet? Okay, that's fine, Sudesh. Just keep on reading through it. There's a direct parallel with what we're going to see here. To summarize, for Sudesh and Jonas, have you gotten that far?
I haven't got the
haven't
book yet.
Yeah, you got to ping me right after class today, okay? Because it'll still be morning for you. I'll stay up and make sure we handle it, okay? Even before I do any of the administrative stuff, I want you to have that. But here's the short version, is that in the 1700s, some pretty bright people realized that with the Industrial Revolution and the fact that they were able to do things a lot more quickly, that they could take a loom that had been operated, manually for years and figure out a way to operate it mechanically. And one of the primary things you do with the loom is you have a bunch of different threads of different, colors up above, and then you bring down the colors you want to weave them into the fabric you're making. And you do it according to a pattern because you're trying to make some kind of visual image. Well, this was all done by hand by really bright people who either remember the pattern or have it written next to them, and they would just follow it. And so they turned that into instead of a manual operation, an automatic one. But the big thing I want to stress is that they had this whole assembly that could take a rigid card that had certain holes in it, defining a pattern you wanted to make, and they would drop down these needles holding the thread onto this card with holes. And where there was a hole, the needle would be allowed to go through, and that color would be used in the pattern. If there wasn't a hole for the needle, that color didn't get used. Fine, you can read the book, or those of you who have know what I'm talking about. The big thing to realize, though, is that action of pulling a card in and then dropping the needles down to see where there were and weren't holes, and therefore where we were or weren't going to take in color, a thread of a specific color, that whole action was kicked into motion by someone pulling a lever and then pushing it forward. And when they wanted to repeat that with a different card, with a different pattern, they'd pull the lever back and push it forward, back and forth. Now, eventually they realized we don't even need a human being to move that back and forth. They got a motor that would move the lever back and forth. But the point is, it was a regular initiator, something that said, hey, start doing something now. They would get everything set up, and then something would go, good, everything's set up. All right, start doing something now. And then get everything set up. Good, start doing something now. This is the clock, and it ties everything together. All right, so let's start breaking this down. By the way, how many of you have actually done any formal study of how the CPU operates and the different parts inside it? Okay,
Yeah,
you did, I'm sure, back in your computer, your undergrad degree, right?
yeah, introduction to computer science.
Good. Some of this will be a reminder for you. Okay.
Yeah.
All right. Now let's see if that sharing is working, and we'll pull up my app that I like so much. All right. So there's my horrendous artwork from yesterday. Everybody can see that? All right. So let's go back, and we're going to start to explore the CPU. Now, again, recall that I'm talking about something that is literally 2 inches by 2 inches on the side. So I'm going to obviously expand this up quite a bit. I don't like yellow. That doesn't work for right now. Now, to remind you, we have these input/output devices that can send information in, or that we can send information out on. And when I say information, I mean data. And of course, I mean patterns of ones and zeros. That's what can go in and out. So this whole CPU could also be given a name of the control unit. And it's got a part in it called an ALU. Does anybody know what that happens to stand for?
Arithmetic and logic unit.
Yes, arithmetic, logic unit. This is a part in the CPU. Now, what does it do? First, it does math. That shouldn't be a surprise. Second, though, it does logical comparisons. Now, if we think about numbers, say 4 and 5, what are some of the logical comparisons we could do on those numbers?
Equal to, not equal to, greater and less than.
Good. We'd also do greater than or equal to. We do less than or equal
Yeah.
to.
Oh, yeah.
Is anybody not
those.
familiar with those 6 operators? We have 1, 2, 3, 4, 5, and 6, or comparison. They call them comparison operators. Anybody not seen those before? We all kind of learned those years ago, right? Okay, that's one of the 2 things that the arithmetic logic unit can do. So regardless of where the information came from, data can be put in here and it can return a result. Now, you're doing a comparison, say equal to or less than. So in that case, what comes out is either true or false. That's what comes out. Now, we could think of that as a 1 or a 0. But what do we really know about it on a physical level? When I say comes out, I mean that there's actually a wire coming out of this part of the CPU. There's metal there. If the answer to one of these comparisons is true, what comes out on that wire?
Electricity,
Good. How much electricity?
5 volts.
Bingo. You're absolutely right. 5 volts if it's true, 0 volts if it's false. It all comes back to the fact that way over here, as you recall, we have a power supply and it might take in 120 volts, but it puts out 5 volts and we use that all throughout the system. Part of it comes in to the arithmetic logic unit and it says, hey, anytime you need to send out a 1, take some of this electricity and route it over here. There are also a bunch of wires coming out. Let's say there's 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. This is where, use red, your math answers or results would come out. If the answer to some thing was like 4 plus 5, well, in binary, anybody know what that looks like? It's 9 decimal. What does that look like in base 2?
1, 0, 0, 1.
Absolutely. That's 1, 8, no 4s, no 2s, 1, 1. Good. So it's 1, 0, 0, 1, base 2. So what that would mean, if we started from the bottom moving up, is that we would have 1, 0, 0, 1, and then all zeros from there on out would come out. And as Alexander was saying, what that really means is all those wires would have 0 volts on them, except for this one and this one. Any questions so far? All right, so that's the ALU, the arithmetic logic unit. And again, it does two things. It does math and logical comparisons. So anytime this whole big thing called the control unit needs work to be done, this math, it'll send the data in. Here's data coming in. And it'll, if it's a comparison it wants, it'll get the answer out as a true or false. And if it's math that once done, it'll get the result out as a binary number. Questions about the ALU? All right,
So
go ahead, please.
when you say it does math, what kind of, I mean, what's the principles of the math is doing? What kind of information does it send, and what's the output besides
Absolutely.
being?
What it sends in is actual binary numbers. So for example, on this one that we talked about here, let's expand this a little bit and look at an ALU. And let's say we have over here is input. We have one little channel right here we're not going to talk much about, which is comparison. We'll come back to that for a moment. But here, let's talk about inputs that are math inputs. And we'll say that there's 8 wires. Now, how many there actually are depends upon what the CPU is. Some of them have 32 or 64 wires, like there's a lot. But we're going to look at 8 just because it's a nice, easy thing for us to think with. It's 1 byte or 8 binary digits. So here's how it would work is, let's say there's 2 numbers we want to add together. We want to add together 4 and 5. And this is where we'll get into the details on it in terms of how the clock works. But what would happen is first, the control unit would set up the first number by, from its side, taking 5 volts and applying it where it needed to make a 4. That would be from the bottom up, 0, 0, 1, 0. That's 4, right? And then, of course, all the rest would be 0 as well. And now, when it's all set up with the voltage on there, then the control unit says to this arithmetic logic unit, it says, read the incoming number, please. And the ALU says, oh, what? Okay, I'll pay attention to these wires. Oh, I've got a pattern of 0, 0, 1, 0, 0, 0, 0, 0. Okay, I've got that. I'm going to store that internally. Let me stop using yellow. I'm going to store that internally here in a little internal memory I have. I'm going to put 4 in there. And I'm going to write decimal, so I have to write out that byte all the time. But we know what's stored in there is 0, 0, 0, 0, 0, 1, 0, 0. You following so far? Okay.
Yes.
Okay, good. Now the control unit says, okay, good. Now, don't read those wires. Let me change all this up. Thank you very much. And it says, all right, let me get rid of all this. It takes away all the voltage. There's 0 volts on everything. It says, all right, what's the next number? Well, that's right, it's a 5 right here. And let me set that up with 1, 0, 1, 0. 0, 0, 0. Oh, I think I lost one. I lost one of my wires. And again, you're reading from here down. This is the ones place right here. Didn't mean to change that to red. And this up at the top is, I think, the 16s place up here. And now when all that's set up, the control unit has all the correct voltages on those wires. It says to the ALU, hey, ALU, go ahead and read that data, please. Check what's on those wires. And the ALU says, oh, those wires that I've been ignoring up until now? Okay, I'll pay attention to them. Oh, look at that pattern. From the top down, 0, 0, 0, 0, 0, 1, 0, 1. Oh, okay, I'm going to take that and I'm going to put in this other little memory location. Good. Now, there's another input going in. that the control unit can put in what's the operation that we want to do. Now, this is the point where you would start to look at this thing that we had called the instruction set. Remember that it came from the manufacturer and it had the actual instruction and then a binary pattern. Let's say that the one for add two numbers happened to be a pattern of 1, 1, 1, 1, 0, 0, 0, 0. Who cares what it is? What matters is that it's unique and that none of the other instructions that might be in that set have the same pattern. They're all different. We just need a unique pattern. And when that pattern gets fed in to this input, now the ALU goes, oh, addition, excellent. And it takes these two numbers and adds them together. And now we can start to look at the output. And these are the wires coming out. 2, 3, 4, 5, 6, 7, 8. Same thing coming out. So I'll write output right here. And so it being 9, it puts another pattern on here. It says, hey, CPU, ignore those output wires. I'm not done yet. All right, let me set it all up. All right, so that's a 9, which means I need a 1, 0, 0, 1, 0, 0, 0, 0. Okay, all right, I got that all set up. Okay, hey, CPU, go ahead and read these wires, please. I have your answer. And the CPU goes, oh, look at that pattern. That pattern is 0, 0, 0, 0, 1, 0, 0, 1. I'm going to take that and it uses it wherever it needed it. Your computer program needed to add some numbers together and now it has the answer. Does that expand that out a little more for you, Ellen?
Yeah, thank you.
Good. Any other questions anybody has on that? Okay. Now, unless you get a very unique job, you're never going to be operating down inside the CPU and manually creating, for example, these binary patterns that are going to go into the ALU, or manually retrieving answers from it, or manually putting in these binary codes relating to instructions. You're never going to be doing that. Now, probably never. There are certain jobs in the industry where you're operating what we call close to the metal. It's a slang term, and it just means very close to the CPU, if not actually operating in it. Those jobs are extremely rare. But I want you to understand what's happening under the hood. All right, so big picture again, we have this control unit. You know, the one thing missing from this little application is something that will just hover over and call attention to a specific spot in the diagram. I'm going to see if I can find a different alternative. Like, I wonder if I circle something. Okay, that's fine. Okay, I'll figure something else out. So big picture, remember we have this control unit right here, and the control unit, among some of its major parts, has the ALU. And we just explored how the ALU works. The control unit will tell it what's the operation I want to do, what's the input going in, it gets output, and we just explored that. Now let's look at another part. Oh, go back to black. We look at another part of this control unit. Again, we've got the ALU over here. Let's make that really small so we have some room to think with. We're going to have a collection of what are called registers. A register is just a little bit of memory, a memory location that's local to the control unit. It's local to the CPU. It's not the kind of memory we were talking about before. It's just, where can I store some binary information? That's all. And there are 3 of them that we care about. One is called the accumulator. It's for storing math results. Remember I said that we might actually have that answer of 9 come back? It would be put into here temporarily until the CPU is ready to send it to an output device of some sort, or to use it in some other operation. That's one register. Another register would be an address register. Now, this stores memory locations. Now, one thing I didn't really totally stress yesterday, but is worth reminding you of, is when we talked about this random access memory, we said that it would be a device that you could essentially think of like a big giant grid of memory spots. And I used the gross simplification that one could identify by the X and Y axis a specific spot. That's not really how it's done. There is no XY axis thing you'd think of. Instead, just like a house number, every single spot you can have in here, a memory location, has an address. It is a unique identifier. And it's just a number. All the memory you can install. Some people have machines with a tremendous amount of memory, like 64 gigabytes of memory. Giga meaning a billion, and byte, as you now know, meaning 8 bits. That's a tremendous number of memory locations, and every single one has a unique number that identifies it. They call those addresses. Any questions about that? Okay, so if we go back up here to these registers, these temporary memory locations or storage. I'm going to say that again. Actually, that's not the way I want to describe those. They are rather temporary storage locations. That's what they are. One of them we already talked about. It's this accumulator. That's where we store math results until we need to use them somewhere else or send them somewhere. And the other one is an address register, and it stores memory locations. Now, there's only 2 types of things we want. We either need to locate some data, or we need to get an instruction. Now, what do I mean? All right, so let's expand something really important about this concept of RAM. Here you are, and you wrote a program. And it is a consecutive series of instructions. Where is it? Where does it get put? It gets put into RAM. Literally, you can think of it this way. There might be different stuff going on under the hood. It's not honestly very important, but just think of it as every instruction for your program gets put in consecutive adjacent locations. Well, the CPU needs to know at any point in time, hey, I could be told to execute the next instruction at any moment. Where do I look to get that instruction? And what it does is it has in this address register an actual number, which is a specific location in memory where the next instruction will be found. Now, other times we've got the instruction, but we need data. Okay, well, let's look at our RAM here and go, all right, over here, we've got a bunch of data stored. How it's organized in the RAM isn't that important, but we might have received an instruction to add together two numbers. Well, we need the location of the first number. So that actually put in here a number, put into the address register a number that says, hey, the number to add, the first one is right here at this exact memory location. Go get it. Okay. Once it's done with that, a different number will be put in here. To get the second number, it would go, all right, that one happens to be right here. Okay, I got it. So that's all that goes in this address register is locations in memory where you need either data or the next instruction to be performed. And again, those instructions, when they get pulled out of memory, all they look like is these patterns in the instruction set, like this. When you write your program and it gets turned into quote unquote machine language, which you guys all illustrated so well in the very first essay, when it gets turned into this machine language, it's just literally a series of those binary patterns, one after the other in memory. And that is your computer program. Questions so far? Okay, good. So I said that there were 3 different kinds of registers. The accumulator is very obvious. It's got a very dedicated purpose. We're going to store math results in there until they're needed somewhere else. The address register is going to hold the address of a specific memory location. That is either telling the computer where to get the next instruction or where to get the data it needs in doing some work. The last one is just called a storage register. And this is literally just a box where you put any data that the CPU is going to need almost immediate access to. It might be data that just came in from memory, but we haven't done anything yet. It might be data that's about to be sent out to memory, but we haven't sent it yet. We can just store it right there until we're ready to do something with it. Right here on the screen, you see, and I want to remind you of the purpose of a computer. We see all the things needed for a computer to accomplish its purpose. What's the purpose of a computer from session 1?
To take in data and then make a change to it and then output the data.
Bingo. The CPU, we already know, has input, output wires that come in and go out, so it can take in the data. And now we know that it can do things with that data. It can either, you can put it in this storage area and then send it out to store it somewhere in memory. We know it can be given a specific instruction on what to do with that data. Having been given that instruction, it can then get the actual data. And if it's a math operation, it can be given that instruction, can go over to the ALU, it'll do the math, and the answer will be stored here. And when everything's set up and done, the CPU can send it on to an input-output device or onto another computer program. So the take in data is accomplished, the process data can be accomplished, and the send the data on can be accomplished, all by the central processing unit. And all it really needs, if you look at the CPU here, being in charge, it needs input devices coming in. It needs RAM as sort of a temporary memory device. And that data can go back and forth too. It needs non-volatile memory. This would be like a drive. And you're kind of there. That's a computer. Oh, and it's got wires to send to outputs to things like monitors or other computer systems. There you go. There's a computer with like 5 parts: input, output, CPU, memory, and persistent or non-volatile storage. So, any questions so far? All right. Now, I've talked about the fact that the computer sets stuff up and then does something, and then sets stuff up and does something. But what we're missing here is the exact cycle, because it's the same every single time. And this is what's called machine cycle. And the machine cycle is 3 steps. 1, fetch an instruction. 2, decode that instruction. And 3, execute it. Now, it'll fetch the instruction. From the spot in memory stored in the address register. It'll go get it. It's out here in RAM somewhere. That's fetch. It'll decode it because built into the CPU is the instruction set that we talked about right here. It's literally physically built into the CPU. It says this exact pattern equates to do an addition operation. This other exact pattern equates to move information into a memory location, and so on and so forth. This other exact pattern, blah, 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 means send something to an output wire. Now, there's a lot of nerdy details, and people who design chips would probably be yelling at me right now. The concept is there that the decode step is just simply, hey, we fetched an instruction. Now look up in the instruction set what that is to do, and now perform that exact action. I want to show you now an actual reference. It's linked inside what I gave you yesterday, but we cleared up enough of the terms that we can go through it and get into a little bit of nitty gritty. So I'm going to stop sharing here. Put that back up to charge. And then let's look at this reference here. All right. There's a couple things I like about this. 1, it's very accurate. 2, it's really ugly. It's like very, very early 2000s. Notice it refers to a CD-ROM, a read-only memory device, which I haven't seen one of those in years. But it doesn't matter. All the concepts are there. So let's look at this diagram. And frankly, it's a little crisper and clearer than any diagram I would make. And we'll make sure that some of these terms here get covered. Now, one, input and output, you can think of them as sort of channels into and out of the device. Every single channel in or out is numbered, and there's a special word for them. It's ports. You might have a port with the number on it of 3000, another port on it with the number of 80, another 443. All these are numbered ports, and they represent an individual connection in or out of the CPU. Well, of the computer. Then, of course, we have the motherboard and the CPU we've been talking about a lot. There's also on the motherboard some read-only memory. Now, we haven't talked about this a lot. Does anybody have any idea what this read-only memory is all about?
We use it for when we reboot our computers.
When we do what to our computers?
When we reboot.
Reboot.
Yeah.
Genius, Jonas. Okay, good. All right, so let's just talk about this for a second. Read-only memory means exactly that. You can only read from it. You can't change it. Random access memory, you can change the information in it. What goes into read-only memory are permanent programs and data. Stuff that's not going to change. This is a simplification, but stuff that isn't going to change for the life of the computer. And one of the things that won't change for the life of the computer is when I first turn on the power, what do? Here I am, I'm a CPU. My job is to fetch instructions, decode them, and execute them. Where do I start? And so what Jonas is talking about, this concept of booting up the computer, we've all heard it. Does anybody know what the origin of the term boot up the computer is? There's an American or English idiom, a phrase whose meaning isn't literally what the words are. There's an English idiom called to pick oneself up by one's bootstraps. And it literally comes from a period in about the 1800s in America when people wore boots and they would have straps on the front and the back. And boots were very hard to put on. And you'd have to grab the bootstraps and pull them to pull a boot on. But the point is, you didn't need someone to help you put your boots on. You could do it yourself. That's what bootstraps were for. Prior to that, people would literally have a manservant who would help them put their boots on. So that's a bootstrap. And we took that term, it entered the common English language to start to mean basically to get yourself moving or started on something without needing some external force to kick you in the rear and get you moving. It just meant that in common conversation. You know, someone who showed a lot of initiative could be described as, you know, he can pick himself up by his bootstraps. And we stole this term and used it in the technology industry because we needed a way to describe what happens from the moment you turn on the computer and start bringing electricity into it to the point where it's up and running and ready for human interaction. Because it needs to do that without human interaction, it needs to get up and running without human interaction, they call it bootstrapping the computer. In other words, the computer gets itself moving and ready for work without human intervention. And it got shortened to boot the computer or boot up the computer. But that's the origin of it. And the way it works is in this ROM, is a tiny computer program. And the very first instruction of that computer program is literally coded mechanically into the chip. When the chip first receives power and starts its very first fetch, decode, and execute machine cycle, already built into that address register is the physical location over here in ROM of the very first instruction. And so the computer, without human intervention, knows where to start. And as long as it knows where to start, well, then it just keeps moving through this program one step at a time. Any questions about that? Now, there's a specific name for that computer program that is the first program that gets run when you first turn on the computer. Does anybody know what that computer program is called? Anybody ever seen the term BIOS? Well, there's no G in it. BIOS. Has anybody ever heard that term before? Yes, no?
Yes.
Good. Anybody else?
Yeah.
Okay.
Oh.
Anybody know what it stands for?
Systems. Yes.
It stands for Basic Input Output System.
Mm.
It's literally the first computer program ever installed on any computer. And it isn't even installed by a person. It's mechanically installed when they create the motherboard. They physically create a little teeny chip that has all the instructions for the program in it. And then over in the actual CPU, inside that address register, they make it so when power comes on, the actual information right inside there is the location of the first instruction in that BIOS program. And that way, when you flick the switch and turn your computer on, the CPU gets power. It looks inside that address register. It says, oh, let me reach over to this location inside this RAM that I have and grab that instruction. I'll decode it because my instruction set is on me. And then I'll do what it says to do. And after that, we're off to the races. The CPU will just keep looking in at those instructions over in ROM, those instructions that are the basic input output system program, and it'll keep doing them. And when that program is finally done running, it gets your computer to the point where it can actually run the second most important computer program that you have. And that's an operating system. We'll talk about that later. The most important program is this one you're looking at on the screen. Without that built-in program that you don't have to do anything to get it to run, your computer is just a big old hunk of metal and plastic. But with that program physically installed in that read-only memory, now your computer can actually turn on and start doing stuff. Okay, good. So that's why they call it boot up the computer. Any questions? All right. So let's start talking about how are we doing time-wise. Perfect. All right. Let's start talking about this this thing that I said is the most important part of a computer called the clock. Can anyone tell me what a clock is as regards a computer? And when I ask these questions, I don't very often expect someone to know the answer, but I just want to check and make sure I'm not talking over anybody. Anybody have an idea what the clock is?
I think I remember from the book, it was like sets the timing for when the CPU receives instructions and then performs them.
Yeah, That's a great description. What I really like about the description is it is very simple, and I actually mean that as praise, right? It's a simple thing. It just sets the timing for when the CPU does its job of grabbing an instruction, decoding it, and doing the work. That's all it is. Let's look at that in a little more detail. And this is something that's best understood graphically. Fire up. I wonder if I stopped broadcasting. I did. All right, here we go. All right, good. I was about to say I get a little bit nerdy about clocks. Well, let's face it, I get nerdy about a lot of things. So let's talk about the clock. First of all, just to give a little bit of mass, if you have the motherboard, typically you'll have the CPU on here, and separate from it will be a little teeny tiny device. That's the clock. Now, sometimes computer manufacturers will put that on the actual CPU. Doesn't matter where it is. What matters is its function. What is it? It is, first of all, an electronic device. It puts out electricity. And say, this is important, at a constant frequency. This is important. So let's talk about frequency for a minute. When you talk about electricity, there's either constant voltage. We've talked about that before. We could say something's either at 5 volts or is at 0 volts. And we want it to stay at 5 volts as long as we need it to be there for it to represent information. And we need it to stay at 0 for as long as we need it to stay there to represent information. Remember, that's a 1 or 0. That's a true or false, so on and so forth. That's constant voltage. They also have a term for that called direct current. And that's opposed as to, or that's as opposed to varying voltage, otherwise known as alternating current. Now here, if you're going to measure voltage over time, it might look like this. It's got a positive part to it and a negative part to it. This is just one example of what it might look like. And this is actually kind of what the electricity coming out of your wall looks like. It goes up and down and up and down and up and down. Although, be a little more weird about it, it actually goes up. Wow, that was a horrible diagram. Like that, there's 3 signals. Go up and down like that. All 3 of them taken together end up being, at any one point in time, about 115 volts. That's a separate thing. But the point is, electricity can vary in voltage. The voltage can go up and down. Any questions about that central concept, that we can set up machines where the voltage goes up and down? All right. Now, in computers, we do need varying voltage in one specific thing. We've already said that we don't want varying voltage when we're representing data, but we do want it to tell the CPU to get to work. And this is how it works. We have a little teeny device called a clock, and it puts out electricity. There's a positive. That's a positive. Nice. And it comes out of it on a wire. And if we were to look in here with a microscope, there's a microscope. We look right on there and measure it. It would look like this. And I have a grid here, so I'm going to be very precise. And so on. The top of this could be 5 volts and the bottom could be 0. But here's the important point. This is a constant frequency. The rate of cycling is constant, does not vary. Now we need this for a very specific reason. We want to set it up so that every time, I put this in green, we go from 0 volts to 5 volts on this wire, that this wire goes into the CPU. We're going to call this the clock signal. And when that signal goes from 0 to 5, that tells the CPU, start the machine cycle, please. And what are the 3 steps to that machine cycle?
Decode
Fetch the
it.
instruction, decode the instruction, and then what?
Execute.
Execute the instruction. And it needs to do all of that before the next jump from 0 to 5 happens. Because at that point, the whole cycle needs to start all over again. And so it goes, literally billions of times every second. This exact uptick happens in a modern computer between 2 and 4 billion times every second. And in this way, we have a constant signal into the CPU to just do the next instruction, please. Please get to work on an exact regular basis. And people recognize this when they're making computers, and they had the question, well, how can we have a constant frequency? And in the beginning, they literally couldn't build electronics that were constant. It didn't work. So they actually found, and this is going to sound weird, they found a crystal in nature. There's several of them. There's a kind of crystal that has this really weird effect. You take the crystal and look. I am not an artist. Here's a crystal. I'm just going to write a diamond, okay? Fill it in. There it is. And we're going to take a wire that comes in and goes out. I'm going to put a little teeny bit of electricity on it. And now we're going to take two little arms made out of metal. A device that will squeeze them towards each other. Like it squeezes inward, like that. It literally puts pressure very delicately on the crystal. Now, this all seems really weird, but the reason why is they discovered this certain kind of crystal, if you squeezed it at the exact right pressure, would physically vibrate at a constant frequency. It would literally be held in there and it would be shaking back and forth internally without breaking. It would last for years, if not long, thousands of years. It would just sit there and could stay that way indefinitely. And that meant that the electricity going into it would go in at a constant level and come out vibrating because of the physical vibration of the crystal. And it was at perfect, exact frequency. And they installed these inside of a computer. I'm going to draw it a bit bigger because they were kind of big. You'd have this crystal. And the signal from it would go into the CPU, and that was our clock. This kind of crystal, the word for it is piezoelectric. You'll see that word when you start studying computers, and this is why. Now, who discovered that there were kinds of crystals that you could do this with? I don't know. I'm pretty impressed and blown away. It was a very creative way to solve the fact that we need an absolute, perfectly reliable signal going into computers. We need this. It has to be absolutely unvarying. The moment it varies, we risk something. What if it goes from 0 to 5 volts a little bit too early? And the CPU has not set everything up, finished with the previous instruction, and set everything up to be ready to grab the next one. Your computer breaks. It doesn't know what to do. It's grabbing the wrong data. It starts fetching and there's no instruction, or it does the previous instruction twice. It's a nightmare. This signal has to be exactly, perfectly the same every time, which my handwriting isn't. That's what a clock is for. Any questions? Okay. So I kind of referred to this earlier, but the thing we were talking about was this thing in the book called a Jacquard or Jacquard. I don't pronounce French well, sorry, loom. And you would literally have up at the top of this big structure, a bunch of needles, each one of which was connected to a spool of different colored thread. There's the spools, and the needles could come out of them. You would feed in a card. The cards were made out of really durable material, and they would have some sort of a pattern on them that showed which colors you want. So that gets put right here below the needles. Over here is a big old lever. When the lever is pushed in one direction, all the needles come down, and where there are holes, that exact needle can come through. If there isn't a hole, no needle comes through. And that means that down here, which is, I'm going to try to draw a piece of fabric being made, think of like a rug. We'll take the blue thread. This means the blue thread is going all the way down through that hole and through this needle and gets put as the next row of color on your blanket. It could mean that the wrong color, this needle for red also had a hole. And so it comes through all the way through, and we run a red in there as well. But the point is these cards. These cards are Boolean. In other words, they are true or false logic. Because where there is a hole, the needle comes through. Where there isn't a hole, the needle doesn't come through, and that's all there is to it. And this lever over here, that is our clock. When it moves in one direction, the whole cycle happens. We basically, you can think of this card as this is our instruction. And this whole giant machine will do the instruction that's programmed on the card. That's a computer. That's everything about how a computer works. You can think of this card as the instruction register. That's where we store the next instruction to be done. And we have a big old chain of them. Literally, they were connected by chains, all being fed into the machine. Now, those of you who've read the book, you kind of saw that illustrated, but I also just want to tie it back to what we just learned. All right. As we move forward into computer technology, we're almost done. We needed to get data into a computer, and we need to get instructions into a computer. And we did it with actual cards. Has anybody ever seen a punch card? Like physically seen one with their own little hands?
Does it look like the
I have.
one used in Barbarian organ?
Say that again.
Is it the same kind of punch cards in this organ that you turn and it makes music?
It's a very, very, very similar concept. Yes. This is a computer punch card. I wish I could turn this. You can see how we're organizing things into rows. I want to see one that actually has holes punched out, though. There we go. Where the black is, they've punched holes. That means a true. Where there aren't black, it's a false. Or true, you know, where there's a hole, there's a 1. Where there isn't a hole, it's a 0. This card would get fed in one row at a time. Like you see the zeros, those are all one row at the top. The card would get fed in a tiny little bit. Literally, needles would come down. And if they could go through the paper, they would make electrical contact and pass on 5 volts. If they couldn't go through, they would, if there wasn't a hole, it couldn't go through, and they would pass on no voltage. And that's how you would get the pattern of no voltage, 5 voltage, no voltage, 5 voltage. This is how we put instructions and data into a computer, these punch cards. I'm illustrating this not because I'm a bit of a history nerd, although I am, but just to show you that we are doing all these things electrically now with these really fancy computers, but they all translate back to real world physical things occurring. And because it's so small and you can never see it happen, and it doesn't have any moving parts anymore, it can be a little bit hard to picture it in your head. And so I want to use this to picture that there are two things we need to give that CPU, either an instruction to perform or the data to perform the instruction on. We literally use these physical cards that are binary cards. The existence or non-existence of a whole is a binary concept. If it's a whole, it's a binary 1. If it's not a whole, it's a binary 0. And that's how we fed either instructions or data into a computer. We're doing the same thing now. It's just that when we do it, let's go back up here. When we do it here, those instructions, remember they're over here in memory. We're just pulling in 1s and 0s and patterns, but it's the same exact thing. Or if there's data we need, it's over here in memory, it's still just patterns of 1s and 0s. We don't need anything physical to do it anymore. And we can control with a clock the thing that we used to control by either moving a lever back and forth or, let's see if I can, or moving this card 1 row forward, 1 row forward, 1 row forward. Any questions? All right. A lot of stuff here. I want to make sure I don't lose anybody. Okay. And now, just because I'm so impressed by it, I want to tell you about one other cool thing. I put it in the, see what happened here. Okay. So look at this diagram again. We talked about the fact that the signal, let's do it all in black now, just draw over again. The signal coming out of the clock is exactly precise. We'll even erase the blue one that's a mistake, right? It's a very precise signal. And when, the computer industry was developing personal computers in the 70s, they had these clocks and everybody was building their computers to say, okay, like Eric said, when we go from 0 to 5 volts, that's the signal to tell the CPU to perform another action. So it's just a cool story about developing the first Apple computer. Steve Wozniak, absolute nerd, realized that they had the monitor that they had to think about. And they had to worry about creating images on the monitor. And if they had to rely on every single one of these upticks to do instruction, that their computer is going to be really slow, especially as regards putting things on the monitor. So Mr. Genius Steve Wozniak, in one of those moments where you're like, afterwards, duh, decided to make it so sending information to the monitor was not something the computer did on this uptick. Instead, as a completely separate circuit, he designed it so it would detect this drop from 5 volts to 0. And then the CPU would do any image creation on the monitor. So it could do all the calculations and data stuff on the up and all the image stuff to the monitor on the way down. And he doubled the speed of his computer with one tiny little conceptual change that just blows my mind. Because all you need is a change that's reliable. 0 to 5 is reliable, happens at the exact same timing, and 5 down to 0 is reliable, happens on the exact same timing. All right, so that's the material we have, okay? I wanna have sufficient time for Q&A. We went through a lot of stuff. And then I wanna talk about the homework and get any questions answered about what the homework is, because while we're not gonna see each other physically, until next weekend. Okay. There'll be anytime you want during the week to have a phone call, an email chat, something in Discord, an actual Zoom call, whatever you want. I'll make it work out. But regular class isn't for almost a week. So we'll make sure that we have everything set up. So first, are there any questions so far? Anything at all about the stuff we went over during the evening? Okay. All right. Then what I'm going to do is I'm going to pull these assignments over and we'll talk about them. Okay. First of all, we are going to move everything about binary math to a later date. So I'm actually going to take the binary math part of it out. Do not do this part. Okay. Let me look something up right here. Markdown strike through. How do you do that? Does anybody know what markdown is? When I say markdown, what I'm talking about?
It's like a language.
Yeah, it's a document
Kind of.
formatting language. You can see some of the syntax on it. Like if I go up here, you see how there's this pound and then pound. That's instructions that most browsers and a lot of other computer programs can interpret. They change the appearance. Watch when I go to viewing or reading mode. That just shows the size of the headline. This is larger than this. And you see how this is a bullet pointed list, but when I wrote it, I just did dashes. It's a really nice syntax for creating documents. That's what Markdown is. It rocks. But what I was looking for was how to do this. I'm going to go assignment, and it's tilde, and then tilde at the end. So now that's a strike through. Okay, good. All right. So I do want you to do this essay. Describe the decimal number system to someone who has never used it. You might find that in doing so, you need to simply describe a number system as a concept, using the decimal system as the example to illustrate the idea. If you need to review yesterday's session, do it. But this, I want you to view it as if you could hand this essay off to someone who literally had come from a different culture and didn't know decimal at all, and they could work out what it was. Please take your time on this. The second one should be a bit easier, and you can refer to the earlier one. This essay about describing the binary system does not need to be a standalone essay. You don't need to repeat all the points you made earlier. You could literally make them one big long essay, or you can say, per my previous essay on the decimal number system. It's totally fine. Any questions about those two essays?
Less than 8,000 words.
That was a nice callback. Yes. Yes, less than whatever it takes for you to feel like you've expressed it clearly, you defined your terms, someone could follow along with the logical sequence. Here's the biggest advice on this. Periodically, as you're writing it, adopt the viewpoint of someone who doesn't know what a number system is at all, and look at it from that point of view. Part of the reason I'm doing this is, first, to make sure you fully understand binary and what a number system is, but two, I'd like you to be able to explain this concept to someone in a simple enough manner that you won't get frustrated and they won't get frustrated. Because it's actually come up many times in my career. Like, for some reason, it's kind of interesting. For some reason, people really want to know what the hell binary is and how it works. So it's one more chance to practice your ability to break down a relatively complex subject, or if not complex, at least something that people have hardly ever examined. It's a chance to break something like that down into a simple explanation in its logical sequence that someone else can really understand what it is. All right, this third essay is not a very long essay at all. I just want you to explain why is it that the CPU will use RAM when operating a program instead of a hard disk? Why is it that per that diagram I showed, all the instructions for the computer program that's being run are going to be held in RAM? And why is all the data it needs access to whenever possible can be held in RAM? Why there and not down on the hard disk? That's not a very long essay. And if you don't understand it, you can Google or watch the session from last night again. Then there's just a quiz on the logical comparison operators and describe what the key registers are that the CPU uses and what purpose do they serve. Finally, describe the machine cycle and the purpose and operation of the clock. Besides the very first essays, these other ones are honestly just a brief explanation that follows and shows me that you understand it. Any questions? Okay, cool. All right, I went over yesterday, so I'm going to give you back time, and we're going to end off a little early today. As always, throughout the week, hit me on Discord. Quick housekeeping thing. Let me stop sharing for a second. Let me check something on Discord. Jonas, did you get your invite to Discord?
Yes.
Okay, let me make sure I accept you.
I'm already a member.
Good, excellent, thank you. All right, good. I want to make sure everybody's, so I have everybody, I have all 5 students in that student forum. You're all good. All right, good, excellent. All right, as always, throughout the week, if you have anything at all, hit me up either in the student forum channel or private message me in Discord, and I'll help. If you feel stuck or frustrated on anything, reach out immediately. And if there's anything you want to talk about, just hit me up. If there's anything else, we're going to call it a night or a morning, Sudesh, Jonas.
Okay, thank you.
Thank you all so much. Appreciate
Just
it.
one,
Oh, yeah, of course,
Eric.
Sudesh. Yeah.
the homework,
Yeah.
you put a link.
Oh,
or-
did I send it yesterday? Let me send it to you right now. Let's see. Chat. Yeah, I should do that because I made a tiny little change. I apologize. Let's see if I can send Markdown through here. Oh, didn't I have to turn it into a PDF? I did. It's being stupid and frustrating. All right, let me do that again. That's really rude. It isn't this stupid and frustrating. Let me see if in Discord it will let me send it. Did that send? Did that arrive?
Yes.
Yes.
Awesome. Okay, good. Okay, cool. I'm going to find a better way to put all these files in places for you rather than sending them like this. I'd like to be able to actually, while I'm working on those session notes, have you all be able to look at them in real time. I have no problem with that. I'll work out a better solution during the week. Any other questions? Okay, good. Excellent. Have a great night. I will see you all next Saturday. Sorry. I want to do Sunday, Monday from now on. I like this one day after the other. It kind of keeps the thoughts together. Everybody fine with that?
No, that's totally great.
Good.
If there
And
are
does that work for you,
consecutive
Sudesh? Is that all right?
classes.
Yes, yeah.
Okay, good. All right. I'm gonna make it official. I'll put it out on the FAQ, and it'll be Sunday, Monday every week at 8. Okay, cool. Have a good night, folks.
Have a good night. Thank you.
Thank you.
Okay, have a nice time.